So now what we're going to do is we're going to look at circuits, okay? And we're going to revisit circuits. We did some of this earlier on in some of the course, but now we're going to look at it like a full circuit, right? Where we have inductance, we have capacitance, and we have resistance. Because what they're going to be is they're going to be a second order differential equation, right? Great news, though, is that they're going to be a second order differential equation with constant coefficients. So we're actually, in fact, going to be able to solve them, okay? So what I want you to remember is that the differential equation for a circuit whose charge is Q, so Q is the charge, is going to be given by di dt, okay, plus R over Li plus 1 over LC Q equals 1 over L E of t, okay, where I is the current, right, which is Q equal to di dt, or excuse me, I equals dq dt, pardon me, okay. R is the resistance, L is the inductance, C is the capacitance, and E of t is the electromagnetic charge. So it's basically an EMF, something that's actually pumping something into the system. Now, given the fact that I equals dq dt, okay, what I get if I actually replace all of my i's with q's is I'm going to get q double prime plus r over l q prime plus 1 over LC q equals 1 over L E of t. Okay? This is a second order differential equation. It's definitely something that we could actually solve. In fact, since, right, at least in our model, okay, since they're all constants, we can use, okay, our polynomial differentiator. We can use P of D, okay, in order to solve these, all right? And so, like, let's actually take a look at what happens. I mean, like, let's kind of set these up, put them into, you know, an auxiliary polynomial, and see what we kind of get as a result, because that's going to kind of help us define what's going on with this circuit, okay? So I look at this and I'm going to say, okay, well, first I'm going to solve, right, LQ equals 0, Q being my current, right? And so I get Q double prime plus R over L Q prime plus 1 over LC Q equals 0. All right, that's my homogeneous function. So my P of D is going to equal D squared plus R over L D plus 1 over LC, right? Okay, and that's P of D. And so P of R is going to equal R squared plus R over L R plus 1 over LC, 1 over LC. Okay, so that's all we're going to need to solve, right? Solving this gives us the solution to the homogeneous part. So let's see what happens when we solve R for R, okay? Right, again, we have R squared, okay, plus R over L R plus 1 over LC equals 0, okay? We'll use the quadratic equation to solve for R. So R is going to equal over L, okay, plus the square root of R over L squared, plus or minus rather, R over L squared minus 4 times 1 over LC, all divided by 2, okay, because 2 times 1, right? This is then going to give me negative R over L, okay, divided by 2 And then we have plus or minus the square root of r squared over L squared minus 4 over LC. All right, do a little algebra here. We get negative r over L, okay, plus or minus the square root of r squared minus, r squared C, okay, minus 4L divided by L squared C, okay, all divided by 2. This is now going to equal negative r over L plus or minus, and I'm actually going to be able to pull out an L squared, or 1 over L squared. So it's going to be 1 over L times the square root of, and this will be r squared, and I'm going to divide through by C, and it's going to be minus 4L over C divided by 2. Okay? And so that essentially, that's your function. All right? Now we'll just pull the L down to the bottom, and that's going to give me negative r plus or minus the square root of r squared minus 4, and that's what r equals. Okay, so that's going to give us actually the values for our r. Okay, let's take a look at this. Let's take a look at this and let's examine this a little bit further. So if we have that r equals negative r plus or minus the square root of r squared minus 4L over C, all divided by 2L. Okay? All right, what we want to get is that the kinds of solutions to our homogeneous function, okay, and in fact, the kinds of circuits that we're going to get are going to be dependent upon what happens to r squared minus 4L over C, okay? So essentially, we're going to have 3 options. The first option is that r squared minus 4L over C is some positive, okay, positive real number. And if it's a positive real number, then that means that r is 2 separate solutions. So if r squared minus 4L over C is greater than 0, strictly greater than 0, then r is 2, right, 2 distinct real numbers. All right, and if r is 2 distinct real numbers, what does that mean? Well, that means that we're going to get, right, that y is going to equal C1 e to, well, e to the r1, right, or let's call it negative r, right, plus the square root of r squared minus 4L over C divided by 2L, plus C2 e to the negative r minus the square root of r squared minus 4L over C divided by 2L. Okay, so we're going to have 2 distinct real roots, all right, and so consequently we'll get 2 distinct, right, powers of e, and this should actually EL, ET. This should be functions of t. Okay, so whatever we end up with the r for, right, we'll have both its conjugates, right, that gives us our values. The second option is if r squared minus 4L over C is equal to 0. So that is, if the discriminant in there is 0, then we're only going to have one value for r. Okay, so this is, then r, right, is a repeated root. And so now we can imagine that y is going to equal C1 e to the negative r plus, or just negative r, negative r over 2L plus C2, and then that's t, by the way, C2t e to the negative r over 2L t. And by the way, this is not y, actually, this is q. Because remember, we're looking at q. And particularly, this is QC. It is our complementary solution. Okay, so it's the solution of the homogeneous part. Now, if r squared minus 4L over C then is less than 0, then r has 2 complex roots. It has two complex roots, and so consequently, Q of C is going to have complex solutions. It's going to be C1, and it'll be e to the negative r over 2l. That's the real part. Cosine of, square root of r squared minus 4l over c, actually it'll be the positive of that, right, over 2l. So that's the imaginary part, actually we should say it's going to be the negative of that, so it's going to be the square root of 4l over c minus r squared, t plus c2 e to the negative r over 2l, right, sine of the square root of 4l over c minus r squared all over 2l t. Okay? I'll tell you what, don't memorize these. Just solve for r, right? Utilize what you know about solving homogeneous equations. I'm just showing you what they're going to look like so that you actually think to yourself, oh, I'm actually going to get some different solutions. All right? Now, each one of these has a different way of being described from the perspective of the circuit. Okay? So if r squared minus 4l over c is greater than 0, what we say is that the circuit is overdamped. Okay? That's what we call it. It's overdamped. All right? Now, if r squared minus 4l L over c is equal to 0, the circuit is critically damped. All right? And if r squared minus 4lc, is less than 0, then the circuit is underdamped. So put pretty, well, I don't know, simply, but to synapsize, right, if the roots to the auxiliary polynomial are real two distinct real positive roots, then you have an overdamped circuit. If, on the other hand, that root, there's just one of them, it's a repeated root, then the circuit is critically damped. And if, in fact, that they have complex roots, then the circuit is underdamped. And that's actually how we determine the dampening of the circuit. So now we have QC. All we need to do is go and utilize find QP. Oftentimes the method of annihilators is going to actually work quite well. All right. So we know that Q is going to equal QC plus QP. Okay. QC plus QP. All right. Now here's the thing. QC is called the transient part of the circuit. Transient part of the circuit. It's called the transient part of the circuit. And what we know is that the limit as t approaches infinity, of QC of t is always going to end up equaling 0. All right, you can actually kind of look at that. That's exactly what's going to happen. All right, it's going to end up approaching 0. All right, and what we get, QP, is called the steady state part of the circuit. So what happens is that the limit as t approaches infinity, right, as we keep going on, of Q is going to equal the limit as t approaches infinity of QC plus the limit as t approaches infinity of QP, which is simply going to equal 0, right, because that's what happens to QC, plus simply QP, right? So it's going to end up being QP, right? And hence why we call it the steady state. It's called the steady state because over time, the circuit will approach the particular solution to the differential equation. That's just simply what's going to happen. Okay? So that's going to actually what's going to occur. So hence we got the transient part, the part that eventually fades away to nothing over time inside of the circuit. And then we have, right, QP, okay, which is basically like the solution to the differential equation because you're pumping in, EMF, right? So over time, you're just going to get that steady state, right? You're going to get QP back. Suppose that on a circuit we have an EMF with E of t equal to 8e to the negative 4t with an inductance equal to L equals 2, capacitance of 1/16, and a resistance of 12. What is the charge on the circuit after t seconds? Characterize the dampening on the circuit and state the limit as t approaches infinity. Okay, so let's actually look at this. Let's say, all right, we're going to set it up. So that means that Q double prime plus, and it'll be R over L. So that'll be 12 over 2 Q prime plus, and this will be 1 over 2 times 1/16, 1 over LC, Q equals 1, or equals, in this case, 8 divided by L, 8 over 2, e to the negative 4t. Okay? So when we simplify, we're going to get Q double prime plus 6Q prime plus, and this will be 16 over 2, this will be 8Q, equals 4e to the negative 4t. Okay? Now what we're going to do, right, is we're going to solve the d to get those different parts. So for LQ equals 0, that's going to be, right, d squared plus 6d plus 8, right, is our P of d. And P of r, thus, is going to equal r squared plus 6r plus 8, which equals r plus 4 times r plus 2. So r plus 4 times r plus 2 equals 0, implies that r equals negative 4 or r equals negative 2. Cool. Okay. So QC, our transient part, is going to equal C1e to the negative 4t plus C2e to the negative 2t. All right? Great. Now, what I want to notice here is I can now actually define the dampening, right? If you notice, I've got two real roots. Okay, two real roots. So this is overdamped. All right. Another thing that I actually want you to notice is that if the resistance, the inductance, the capacitance are all positive, that's actually going to mean that each one of these values, right, each one of the coefficients in the polynomial or in R are going to be positive as well. And what that means is that we're going to end up with either two negative real roots, 0 as a root, which is also an option, okay, one repeated root, or two complex roots. What we're never going to have is we're going to never going to end up with positive real roots. We're only going to end up with negative real roots, okay? And so consequently, that transient part, that's why that transient part is, right, is going to go down towards 0, right? The limit as t approaches infinity for this guy is just going to end up being 0, okay? All right, now let's go out and let's solve for QP. So we got QC, let's solve for QP. Okay, so now what we're going to do is we're going to use the method of annihilators because this EMF, all right, is of the right form for us to use the method of annihilators. So since that's the case, all right, I need to look at that, and I want to notice that e to the negative 4t is actually over here instead of my homogeneous part as well. So I'm going to have to make sure that I go in and I modify my trial solution, right? My trial solution is going to end up being modified because my annihilator is in fact going to be, well, it's going to be, I'm going to have a repeat of my annihilator along with my polynomial differential operator. Okay? All right. So I'm going to pick a trial solution, okay? And my trial solution, we're going to call it QP, is going to equal, and it's going to be t e to the negative 4t, right? So that we actually generate something, and pardon me, a t e to the negative 4t, okay? So that we modify, right? We add the power of t, okay, onto e to the negative 4t in order to make it linearly independent, right? But then it also still has the form of e to the negative 4t. Okay. So qp prime is going to equal ae to the negative 4t plus, or ae to the negative 4t minus 4 ate to the negative 4t. And qp double prime then is going to equal negative 4 ae to the negative 4t minus 4 ae to the negative 4t plus 16 ate to the negative 4t. And that equals negative 8 ae to the negative 4t plus 16 ate. Combining all of them into the differential equation, what we get is we get negative 8 ae to the negative 4t plus 16 ate to the negative 4t plus 6 times ae to the negative 4t minus 4 ate to the negative 4t plus 8 times ate to the negative 4t. Now, and that'll all equal 4e to the negative 4t. Now what we're going to do is we're just going to hold on, make sure, and hope that ate to the negative 4t terms, they go away. Well, it turns out that they do. Plus 16 here, minus 24, and then plus 8, they're all going away. So that leaves me with negative 8 ae to the negative 4t, okay, plus 6 ae to the negative 4t, okay, which equals negative 2 ae to the negative 4t equals 4e to the negative 4t. So that means that negative 2a equals 4, and so hence a equals negative 2. So my QP, right, is going to equal negative 2 te to the negative 4t. Okay? So now let's take a look at the combined one and talk about its transient and steady state. My combined function now is going to be Q, my charge, is going to equal C1e to the negative 4t plus C2e to the negative 2t minus 2e to the negative 4t. Okay? Minus 2e to the negative 4t. All right? So what we're going to see is, or what we're going to talk about here is this thing here, this is QC. Okay? And here is QP. All right? So as t approaches infinity, okay, QC goes to 0. Right? So Q goes to QP. Right? QC being our transient state, it goes to 0. QP being our steady state, so that one is what we end up getting over time. Okay, that ends up being the charge. All right, so that actually answers our question, right? There's Q, there's what's happened to Q as Q approaches QP, okay, and that answers our problem. All right, so basically all we're really doing when we're working with circuits is we're solving a second order differential equation with constant coefficients on it, right? So consequently, you should be able to do that from earlier parts that we've worked on, and then we're just adding in some vocabulary. So adding in some vocabulary in order to think about, the physics that's going on, okay? All right, so this completes the lecture.